Welcome to the course called Elements of Modern Physics. So we have been doing nuclear physics, and today we are going to talk about radioactivity. Okay, and we have seen some sort of glimpses of it yesterday, but we'll talk about radioactivity elaborately today. So we have seen that the bombardment of atoms with the alpha particles that had set the platform for the determination of atomic structure, and this was done by Rutherford by bombarding these alpha particles towards this gold foil, thin gold foil, a few hundred nanometers thick, and that made this structure of atoms apparent to the community. So there is also an analysis of the chemical relationships among the radioactive elements that resulted in the discovery of isotopes. I have shown you these radioactive elements in the periodic table on the last class, and radioactivity is undeniably connected to the development of nuclear physics. In fact, a lot of nuclear physics and nuclear engineering they revolve around these radioactivity, and we'll talk about this discovery a little bit, but you have to read some relevant literature and sort of understand that how accidental can it become. And so this was one of the upshots of this discovery of radioactivity, that it was just by chance that it was discovered. And the theory of radioactivity that we are going to formulate will depend on the ability to precisely measure these radioactive changes that take place in the nuclides, and substantiate them by simple equations which govern these radioactive changes, or these, how the activity sort of change with time, or the number of particles of a given radioactive element, nuclides basically, that change with time. And these are going to be some of the discussion topics for this class on radioactivity. So I show you this APS 125 celebration which took place in Feb 25th, 2008, and in which it was said that March 1, 1896, Henry Becquerel, is also called Antoine Henry Becquerel, he discovers radioactivity. That's a picture of Becquerel, and he got the Nobel Prize in 1903 along with this Curie couple, Madame Curie and Pierre Curie. And it says that this, I'm quoting it from the citation of this APS news. It says is one of the most well-known accidental discoveries in the history of physics. On an overcast day in March 1896, the French physicist Henry Becquerel opened a drawer and discovered spontaneous radioactivity. It is written in a dramatic fashion, but then you should look up the history, and it's very interesting. So I elaborate a little bit again from the same APS news article. It says that the story of Becquerel's discovery is a well-known example of an accidental discovery, which is what we have told. Somewhat less well-known is the fact that 40 years earlier, which means that 1856 and so on, because this was 1896. So 1856, someone else had made the same accidental discovery, and his name is Abel Niepce de Saint-Vector. He was a photographer by profession. He was experimenting with various chemicals, including the uranium compounds. Uranium is one of the most radioactive or common radioactive element that one knows. So like Becquerel would later do, means at that time 40 years before Becquerel, he exposed them to sunlight. So these uranium compounds to sunlight, and placed them along with pieces of photographic paper. He was a photographer, so it was natural to deal with photographic paper, and he placed these uranium compounds along with these photographic paper in a dark drawer, and he opened the drawer and found that some of the chemicals, including uranium, exposed the photographic paper. Okay. And Niepce thought that he has found some new sort of invisible radiation, and he reported his findings to the French Academy of Science. However, probably because his profession was not a scientist, that no one actually investigated the effect any further until decades later, 4 decades later, Becquerel repeated essentially the same experiment on these 1st of March. So, this is the discovery of radioactivity. And the properties of radioactive decay are when nucleus undergoes an alpha decay or a beta decay, the Z or the atomic number that changes, and it becomes a different element. Okay. So we have a different element when the nucleus of a certain element that undergoes these radioactive decay, and the energy of these decay processes comes from within the nuclei. That is, there is no excitation from any external agency, it just spontaneously happens. Okay. And it is a statistical process and hence obey laws of probability. And why these this point number 2, which says that where does this energy come from, because there is no excitation that has happened from any external agency, and that was explained by Einstein's mass energy equivalence, that is mass is can be converted into energy, and he wrote down that E equal to mc square relation. So, which means that the mass itself has a form, or rather it is in a form of energy, which gives rise to this decay. Here schematically some different radiations coming out from a radium sample kept inside a lead box is shown, and what you see, those X's or the crosses, these are actually the magnetic field lines that are going into the screen that you see. So, it is into the paper plane of the paper, and then you see all these radiations coming out, and the alpha particle paths are shown on the left, which kind of bend in the magnetic field, and which means that of course they are charged, and the beta particle paths are shown on the right, which has got the opposite curvature and smaller than the alpha particle curvature, and also because it bends in a magnetic field, so there must be the centripetal force that is acting there. So, what we are trying to mean is that we have a mv square over r, and that is equal to the qvb and so on. So, this equation is they are balancing each other. So, there is a Lorentz force that balances the centripetal force, and then there is these radius that tells you that how much is the curvature of this or the trajectory of the particle. Okay. So, these are the beta particle, and then you see that there is a gamma ray has also come out. So, it is alpha, beta and gamma, but the gammas are chargeless and they do not bend in the magnetic field. So, these gammas are the photons, and alpha are of course we know as the helium nuclei, which is written as this 2He4 that we have seen earlier, and these betas are nothing but the electrons, and gammas are the photons. So, this is the schematic diagram of these emergence of radiation from a radium sample. So, different decay processes are, we have from the nucleus, so that is alpha decay, and then there is a beta decay, then there are positron emissions, and then there are electron captures, and then there are gamma decay and so on, and each one is shown by this equation that there is this X with atomic number Z and mass number A. When it undergoes an alpha decay, you see that there is the Z becomes Z minus 2 and A becomes A minus 4. For a beta decay, it becomes Z becomes equal to Z plus 1, and of course, there is an electron that comes out. You also have a helium there. So, and the positron emission, it's just the opposite of the beta decay, or this Z becomes Z minus 1, and you get a positron there. The electron capture, you get so this electron is being captured by this these element X, giving rise to a Z minus 1, and the mass number remains same, and then it becomes a different element Y. You see that X element goes to Y, and so on in every place. That's what we meant by these, it becomes a new element, and of course, both A and Z could change, or A could remain same and Z could change, and so on and so forth. Okay. In gamma, of course, it there is this mass number doesn't change, but there is a gamma that comes out, and each one there is an example given. So, there is uranium going to thorium plus helium, then carbon going to nitrogen plus an electron, that is for the beta decay, and then copper goes to nickel plus a positron, and then copper plus an electron becomes a nickel, then a strontium, and it becomes a strontium and gamma, and so on and so forth. Okay. Now, you see that it's like schematically showing that what are these the penetration power of each of these alpha, beta and gamma particles. So, they are from the radioactive materials, the alpha particles are easily stopped by just a cardboard that we use on our everyday office work. So, it can be stopped by this cardboard. Beta particles which cannot be stopped by a cardboard, but it can be stopped by aluminium sheet, a sheet of aluminium, and the gamma particles are they have enormous penetrative power, and they in fact a thick slab of lead also cannot stop these gamma rays. So, these are various sort of penetrative power or penetration power of all these alpha, beta and gamma particles or this decay. So, let us talk about this radioactive decay equations and sort of discuss what is half life. And we talk about radioactivity. So, we talk about the measurement of activities of a radioactive sample and how they really fall off with time. Okay, so, that is the main thing that we want to know. So, the decay process obeys this decay equation, where RT is the activity at t equal to at some time t, and R0 is the activity at time t equal to 0, and lambda is either called a disintegration constant or it is also called as a decay constant, and you see that it is in the exponent, and it is getting multiplied by t, and clearly because the exponent has to be dimensionless, or rather the argument of the exponential function term has to be dimensionless. So, lambda has the these unit of 1 over t, or if t is in seconds or hours, this should be in hour inverse or second inverse, and so on. So, we also define a quantity called as a half life of a radioactive sample, and it is written as this t half. Okay. The way it is written there, it is defined as the time at which the activity of the element or activity of the nuclide that drops to half its initial value. So, R0 becomes or rather RT becomes R0 by 2, and so this becomes, so RT becomes R0 half of R0. So, at what time it falls into that is called as the half life. So, we can put it in this equation. If you call this as equation 1, then we can put it in this equation and can write down these RT equal to R0 by 2, and then cancel R0 from both sides, because that is not 0. So, it gives you exponential lambda to the power t half, a little bit of a notation that you have to form of your own. It's this entire thing is in the exponent. It might give you a feeling that it is not in the exponent, but it is. So, exponential lambda t to the power half is equal to 2. So, lambda into the t half, which is called as a half life, is nothing but log 2. Log 2 has a numerical value of 0.693. So, t half is equal to 0.693 by lambda. So, if you are asked this question that after how much time or rather this activity of this sample will fall to half, or what is the half life, and you are given the disintegration constant or the decay constant, you can simply use this relation to get t half in terms of lambda, or if you are given t half, you can find out lambda using the same equation. This is 0.693 is nothing but the log 2. So, this activity curve is shown for some radioactive element, and it's sort of the activity really falls off as exponential minus t, and this lambda can be found out from this, and then you can use that lambda to calculate t half. It turns out that t half is equal to 5 hours here. Now, there is another quantity, we will just come to that, called as the average life. So, that is t bar, and that t bar is not equal to t half. We will define what is t bar in this slide. Okay. So, for example, if you take t half to be equal to 5 hours, then lambda comes out to be equal to 3.85 into 10 to the power minus 5 second inverse, and we have simply used this thing that t half is equal to log 2 by lambda, okay, and log 2 is 0.693. But this entire description, in terms of activity makes it a little ill-defined, not really ill-defined, but it is less intuitive. But if we represent it in terms of the number of undecayed nucleides, then it becomes more clear, because now we are talking about number, some number that decays over time, and you can count that number. So, the number dn that decays in a time dt is the product of these number of nuclei, and is the probability lambda dt, and that each one will decay, each of these nucleides will decay in a time dt. So, dn is actually proportional to n, and dn is of course proportional to dt, the time over which you are taking it. And if you take both these things and then take this proportionality constant as lambda, that is also one way of looking at this. And lambda is, as we told, that it is a decay constant, and there is a negative sign because this is decreasing. dn is basically has will decrease, and this negative sign simply talks about that. So, if you try to integrate this equation by writing dn by n equal to minus lambda dt, so you get n of t, which is equal to n0 exponential minus lambda t. Now, this n is the number of nucleides left at a time t, n0 is the number of nucleides at the beginning, that is at t equal to 0, whenever you have set t equal to 0 is, and exponential minus lambda t. Okay. As I was saying, that there is also a mean lifetime, and the mean lifetime tells you that when this number really falls to a value which is n0 by e, that is the exponential. So, nt becomes n0 by e at t equal to t bar. Okay, so, that is the definition of t bar, or the mean lifetime, and if that happens, then t bar becomes equal to 1 over lambda, and lambda we know that is equal to 0.693 by t half. So, there is a simple relationship between t bar and t half. They are slightly different than each other, and makes sense because this E is really something like 2.7, whereas when we define half-life, this factor in the denominator instead of E, it was just 2. So, it is 2 and 2.7 that made the difference between these T half and T bar, okay, which are respectively the half-life and the average life. So, we sort of go back to this activity picture and want to understand that what does this or how these activities connected to the number of nucleides, and R is nothing but defined as the activity is defined as dn dt, okay, with a minus sign, and you can write this down as R equal to lambda n0, which is n0 is the number of nucleides at t equal to 0, okay, and exponential minus lambda t. So, if R 0 equal to lambda n 0, okay, then you get R t equal to lambda n t. So, that is the relationship between the number of nucleides and the activity at a given time, and the same relationship actually holds for all time. So, because you see the left relationship is R 0 equal to lambda n 0. So, the same relation holds at any subsequent times. Let us see an example. The question is that find the activity of 1 milligram of radon, which is written as this 222 Rn. The atomic mass is what we want, is given as 222 units or atomic units, and the decay constant we can find out by taking this 0.693 divided by T half, and this T half is picked up from some data sheet, and that gave you that this is equal to 2.11 into 10 to the power minus 6 per second. So, that is lambda. And now the number of atoms in 1 gram of radion or 1 gram of this Rn radon is equal to this 1 milligram, which is 10 to the power minus 6 kg, divided by its mass, and then you take these mass of this proton, which gives you there are so many atoms at T equal to 0. So, if you want the activity, we will have to multiply these lambda that you got and this, and getting this activity in terms of these decays per second. It also has these units as TBQ and CI and so on. We can restrict ourselves to these decays per second, and so R equal to lambda n, this is 5.72 into 10 to the power 12 decays per second. So, that is the activity. So, that is what is being asked, find the activity of 1 milligram of radon. What are the other applications of radioactivity? So, one does radioactive dating, or these are also called as carbon dating. So, the ages of geological or biological specimens which are very old specimens can be established by radioactive dating. The ratio of the amount of the nuclide and the stable daughter, which is called as a resultant, or it is called the daughter. So, this the parent nuclide, so it is often called as a parent and daughter. So, parent one is the one that is at T equal to 0, and then of course, it undergoes a transformation from that element to a different element, and that is called as a daughter element. And this is it says that it depends in a specimen depends on the age of the latter. I will read it once again. The ages of a geological or biological specimen can be established by radioactive dating. The ratio of the amounts of nuclide and its stable resultant in a specimen depends on the age of the latter, which means the age of this daughter this thing. So, by counting the age or knowing the age, so we can know what is the age of this specimen. Greater the proportion of these daughter nuclide, it is likely that the older is this specimen. So, one can know that approximately how many years old a rock is, and so on and so forth. So, radioactivity is one of the primary applications of radioactivity. For example, rocks, or for example hills and all that, one knows that by doing this procedure how old it is. Let us give an example of such a determination. So, a piece of wood from the ruins of an ancient dwelling was found to have a carbon 14 activity of 13 disintegration per minute per gram of the carbon content. The 14C activity of living wood is 16 disintegration, that is living wood means that this is at the T equal to 0 and so on. So, this is known. So, this 16 disintegrations per minute per gram. So, how long did the tree die from which the wood sample came? Okay, so, that is the question. So, if the activity of a certain mass of carbon from a plant or an animal, so carbon is the constituents of all plants and living beings. So, that was recently alive is R0, and the activity of the same mass of carbon from the sample to be dated is R. Okay, so, these activity R and the R0, which is at the recent, or rather that is when it was where the initial at T equal to 0 is R0. So, they have this relation R and R0 is R0 exponential minus lambda T. Now, to solve for T, that is the age of the these ruins, or this wood rather. So, this exponential lambda T is R0 by R, and lambda T is nothing but a log of R0 by R, and T is nothing but 1 by lambda, log of R0 by R. So, if you know the disintegration constant, if you know the R0 and R, one can find it. And some equations, say for example, let us not worry about that. The decay constant is found to be like this, which is so here one can give this R0 by R is 16 by 13, because it was initially 16 disintegration per minute and now is 13 disintegration per minute, and so on. So, T becomes equal to 1.7 into 10 to the power 3 years, which is like more than 1000 years, 1700 years. That is the the power of this radioactivity that one can really find out from this carbon dating or this radiometric dating. So, what about the radioactive series? There are 4 radioactive series. Each series yield different daughter nuclei starting from the same element. Okay, and why there are only 4? And I mean, what is the justification of this 4 series? So, the 4 series comes from the alpha decay actually reduces the mass number or the atomic mass A by 4 units. So, after that 4 this gets repeated. So, if you take these mass of a certain nuclide to be equal to 4n, so A equal to 4n where n is just an integer. So, they would decay into descending orders of the mass number. So, 4n2, 4n minus 1, 4n minus 2 and so on. And the other 3 series will be 4n plus 1, 4n plus 2 and 4n plus 3. Well, not 4n plus 4, this is wrong. Okay. So, this is written by mistake. So, 4n plus 3, because 4n plus 4 will become equal to 4n, same as 4n. You just go to n from one value to its next value. So, that will be 4n plus 1. So, these are the 3 series whose mass numbers are given by 4n plus 1, 4n plus 2 and 4n plus 3, and where n is just an integer, and this gives rise to 4 radioactive series. So, different members of this series also can decay into one another. We will give example of that. So, the 4 radioactive series, 4n are thorium, which has half life 10 to the power 10 years, very long half life, and the stable end product is the lead 82208. 4n plus 1, it is called neptunium, which has a half life of 10 to the power 6 years, and the stable one is that one gets bismuth. And then 4n plus 2, it starts with uranium and lands with 82206 Pb, and 4n plus 3 is the actinium, which starts with again 92235 uranium as opposed to 92238 uranium for the 4n plus 2 series, and the half life is again like 10 to the power 8 years or 10 to the close to 10 to the power 9 years, and the stable end product is again lead, but with a different mass number as that of the 4n plus 2 series. Okay, so we are sort of closing in this discussion, or rather closer to the end of the discussion on radioactivity, and let's just tell us what alpha decay is. So, the alpha decay is the attractive forces between nucleons are known to be short range. So, these are called as strong forces. Okay, so we are talking about strong forces between the neutrons and the protons. Of course, there are strong forces among quarks, but we are not talking about that. And the total binding energy, say, is proportional to A, which is the mass number, which is equal to Z plus N. Because it's short range, so it will just depend upon how many constituent nucleons are there, and there are A constituent nucleons, which is A equal to Z plus N. Now, the repulsive energy between protons is proportional to Z square. This is, we know that it's just the Coulomb energy, which depends on the charge of these protons. So, for a number of nucleons to be larger than 210, the Z square will be very large, and it will be so this enormous repulsive energy between the protons would be unable to, or will fall short of compensating the attractive potential energy between the nucleons. Okay, and alpha decay actually occurs in such nuclei, and whereby decaying this alpha particle, there is an effort to reduce the size and hence make these resultant element to be stable. Okay. So, alpha decay it's a spontaneous thing that happens for nucleons, the mass number to be larger than maybe 200 or so, and the alpha particles are emitted, which is like 2 He4 are emitted. So, the atomic number goes down by 2 and the mass number goes down by 4, thereby it transforms into a different element and a smaller element, and this smaller element means that there is a reduction in size of the element, and that contributes to the stability, and that is how it counters being coming into a collapse by emitting these alpha particles. So, why alpha particles are emitted, not protons? Because protons can also be emitted. These are charged particles, and so now for escaping the nucleus, one should have sufficient kinetic energy, and we saw it yesterday that if the electron has to reside in the nucleus, its kinetic energy is of the order of 60 MeV. So, the alpha particle and electrons are of course different, but nevertheless alpha particles among the nucleus are the lightest ones. So, they would have very large kinetic energy, which would allow them to escape, whereas protons have much larger mass. So, they have lesser kinetic energy for them to, or rather it's not, as we have told that it's of the order of a few MeV, and that's not the energy with which the protons can escape the nucleus, whereas the alpha particles can escape. So, there is this empirical relation. Energy of the alpha particle is like A minus 4 divided by A is the atomic mass into this Q, where Q is known as the disintegration energy, defined as Mi minus Mf minus Mx into C square. That's like the effective mass or the total net mass, and it's multiplied by C square, that gives you the disintegration energy. Mi is the initial mass of the nucleus, so this let's call it as Mi, and then Mf is the final mass of the nucleus or mass of the final nucleus, and Mx is the particle mass, and so this will tell you that what is the kinetic energy of these alpha particles in a certain nuclei, and if you calculate these will come out to be much larger than about 3-4 MeV, which is the energy that the nucleus can hold. Now, this picture could be familiar from the first course on quantum mechanics or whatever has been discussed even in this course as well. So, there is this potential that these alpha particles feel, and it is based on this tunnel theory. We are not doing any explicit calculations here, but if you see this left region, that is this region here. So, this is the region that alpha particles cannot escape from this region if they are there. Okay. And the alpha particles also cannot enter this region, So, this region that they cannot enter because their energy is lower than the potential that the alpha particles face. So, if they are either coming from this side, then if they are coming from this side, they cannot enter into the nucleus, and if they are inside the nucleus, they cannot come out of the nucleus, and the energy is shown by the dotted line. So, this is classically an alpha particle would not have been able to come out, but then we know that it is inside the nucleus. It is like a wave, it is like a propagating wave. Now, when it enters into the classically forbidden region, it kind of drops, and then it goes on again as a propagating wave outside that barrier, when it acts like a free particle, nearly a free particle, because the energy is larger than V. So, V is given by this dark line, which is the nuclear potential that exists. Okay. So, this is the tunnel theory, and we have done problems on tunnel theory. We of course haven't kind of taken this equation, but this is like an approximation of the Lennard-Jones potential, and the form here is a little difficult to handle, whereas we have talked about say for example, we have talked about this kind of a barrier, and we have talked about barrier of this kind, and so on. Okay. So, these are called step, these are called barriers, but it is something similar to that. So now what's beta decay? So one is that the electron energies observed in beta decay in, of a particular nuclide are found to vary continuously from 0 to a maximum value of maximum kinetic energy value, so Ke max, which is a property of the nuclide. Okay, and let's not worry about this thing that so this. I haven't included this thing here, but the maximum energy of these beta decay is E max is equal to the rest mass energy and this maximum kinetic energy. So that's carried out by the decay electron is equal to the energy equivalent of the mass difference between the parent and the daughter nuclei. Only seldom these, however, there is an emitted electron is found with an energy which is equal to Ke max. Okay, so this actually is taken from Beiser. You can read this book. There is a very nice book on modern physics. And so when the direction of the emitted electrons and of the recoiling nuclei are observed, they are almost never exactly opposite as required for the linear momentum to be conserved. And then the spins of the neutron and proton and electron are all spin half. So, if the beta decay involves just a neutron becoming a proton and an electron, the angular momentum is not conserved. So, beta decay poses a big problem in terms of conservation of charge, linear momentum and angular momentum. And there is this attempt by Pauli to remedy of this in which he said that if an uncharged particle of a small or a zero rest mass and spin half is emitted in beta decay together with an electron, that's what happens, then the above discrepancies would not occur. So he said that there is another extra particle that's emitted, which is later called as a neutrino. And once you take into account the neutrino, there is of course anti-neutrino also that should be found, but never found. And the beta decay is actually given by this equation where the neutron decays into a proton and an electron and an anti-neutrino. So these anti-neutrino is shown by these nu bar, and these will these things that we have talked about, that it violates charge, linear momentum and angular momentum, they are now valid, or rather they would be satisfied. Finally, gamma decay. So, a nucleus is in its excited state can return to its ground state by emitting gamma rays, and these gamma rays are, we have seen, then they have high penetration power. So, they have energies which are the difference between the so there are two levels, and if a nuclide actually makes a transition from the first excited state, let's write it by 1 and by 0. So, they would emit a gamma which is having an energy which is the E1 minus E0. Okay, so, the gamma rays have these energies of the order of MeV, and as I said earlier that they have high penetration power. Finally, some diagram showing from this magnesium 1227 magnesium that decays into aluminum 1327 by these beta decay, and finally it comes from these level that you see here to the ground state, which is or lower state, which is 1327 Al. And by a gamma decay and so on, or it can also do a beta decay to a lower energy, and the difference between these energies is approximately of the order of 0.2 MeV. So, there are these successive beta and gamma emissions shown from these 1227 magnesium to 1327 Al via this 1327 Al. Okay. So, we will stop here with this radioactivity. It is mostly description given of these phenomena. You would like to read more from various books. One of them is, as I said, is Beiser. Then there is another book called Kaplan. These are nice books on these nuclear physics, and one can look at them. We will do another topic which is the nuclear models, and we'll close this discussion on this nuclear physics. Okay. So we stop here. Thank you.